Hi there! So, in the last two videos we calculated the gradient of the loss function with respect to all of the parameters in our neural network. In this video I will explain how we can do the computation for m many samples at once, where m is the number of samples in our mini batch. Because right now, as we have made the calculations, we would need to do the forward pass and calculate the gradient for each sample individually and then take the average at the end, which is much slower than if we were to pack all of the samples in one big matrix and then pass the matrix through the network. And then also do the backpropagation in one big matrix multiplication step. But how this exactly works is what we will be looking at in this video. So, let's dive right in. Okay, I've just said that we will pack all of the samples into matrices, which means that from now on our x, which previously was just a column vector, is now going to be a matrix where we append all samples into the different columns. So x is a matrix that has d0 many rows and m many columns. And the same goes for our targets. Now y, I will also write it as a capital Y instead of a small y to indicate that it has become a matrix. Y is now a matrix with these dimensions, dl times m. And now we can extend the definition of our neural network, because now we want to make the definition as such that we can pass in matrices of an arbitrary dimension. So neural net is still the tuple of dimensions, functions, a layer size, a list of weights and a list of biases. I don't remember the exact order, but this is all the parts we need. And this is now a function, so instead it being a function from d0, it's a function from the space of matrices d0 cross m onto the output space or dl cross m. And we want the mapping to be such that for each additional column that we append into the input matrix, it should be the same as if we were to append the output of the previous neural network definition onto the output of this neural network. So what I mean by that is that we want neural network of x with the new definition to be the same as the tuple where we pass each column into the individual entries of the old definition. But luckily for us, matrix multiplication already does this in a pretty natural way. So we don't really have to change that much about our definitions. And you can verify for yourself that this is indeed true for any matrix multiplication. But well, I still have done a little visualization here, which should help the intuition, hopefully. So what I have here is a matrix WL, and I have the activation matrix AL. And with AL, I am referring to the matrix which gathers all of the activations AL for all of the samples that we have. And here I'm writing the sample number here on the left, which I will keep doing throughout this video because there's not enough space for all of the indices. But if we take A0, for example, this is just the same as our input matrix. And x1 in this case is the first column here, and here w1 is the first row of w. And now if we look at the matrix product of wl and al, then what we see in the resulting matrix here is that the first column here is only dependent on the first column of the second matrix we multiply wl with. So all of the values here only get multiplied with these values. And it's the same with all of the other columns, which means that matrix multiplication really gives us exactly the property that we can append the matrices in the input space and then take the matrix multiplication, or we can take the matrix multiplication individually and then append it in the output space, and it gives the same matrix. So with this in mind, let's actually write down the new definition of our neural network, or finish what I've started here. Let me copy that to have a bit more space. Okay, so now neural network takes an input x and maps it to the concatenation from L equals 1 to the capital L. And we're concatenating all of these functions again. And now z has become a capital letter 2 in order to remind us that we are now working with matrices instead of vectors. And now where z of A, of the matrix A, is defined as the matrix multiplication with A. And now we want to add the bias to every sample, which means that we will construct a matrix which contains the bias in every column and then add it to the result of this matrix multiplication. So what we will be doing is to have the bias here copied over into all of the columns. Now in Python, our NumPy library does this automatically for us, which means that we don't have to worry much about this, but well, mathematically we have to duplicate it. So as you can see, basically nothing has changed to our definition except that we have to copy the bias and that we extend the input and output spaces onto matrices. But the x is again our A0, which gets mapped onto W0, A0 plus the bias. And well, I won't write the copying of the biases. This will be implicitly done in the plus, in the addition. This here is then Z0, which gets mapped onto A0, which is F1 of Z0. And F1, it was component-wise previously, now we apply it to every component of the matrix. So we continue this until we arrive at FL of ZL-1, which is Y hat. Alright, now it's time to extend the definition of our loss. And as I mentioned already, we want the loss to take the average between all of the losses of the individual samples. So what this means exactly is that the new loss function will now be a function from the extended definitions of the neural network. So all of the neural networks which go from D0 cross M to RDL cross M. And it also takes an input matrix and an output matrix. So that's the input space. It takes a neural net, an input matrix and an output matrix, and it maps that onto, once again, a single positive real number, which is the average of the individual losses of the samples. So what we can write is that neural net x and y gets mapped onto the average 1 over m times the sum from k equals 1 to m of the losses of the samples. And I have introduced a new thing here, which is this lk. And with the k here, I want to indicate that we're taking the loss of the kth sample. So every time you see a k on any loss function, you know that we are referring to the loss of this specific sample. And now again, we are constraining our loss function to be the result of some measurement of the distance between two vectors, or more specifically, the average of all of these distance functions. Okay, and there's one more way I want to write this down, namely omitting all of the arguments. So you will also see me write it down like this, where we only have this number here. Now let's continue our calculations. So I have already said that the X has become a matrix, our ALs have become matrices, our ZLs have become matrices, etc. Now there's one last thing we have to define, which works a bit differently, and these are the errors. Because now we want to also peg the errors into a matrix. But our errors here, they were row matrices up until now. But for the rest of the calculations, it will be actually easier if we peg all of these errors also into columns and not into rows. So what we will do is that we will define, and honestly I'm making this delta up. I don't know if this letter exists in that writing style or not, but I like it, and so that's what I decided to go with. So we will define this capital delta as all of the deltas of the kth sample in our mini batch, and we are transposing them actually before we peg them into a matrix. So we are transposing every individual entry in order to make up this new matrix. And another thing that's just notation is that from now on, every time that I write only one index next to a matrix on the bottom, then I'm referring to the ith column and not the row. If I want to refer to a column, then I would write a dot next to it, because the dot signifies that we are taking all of the columns, because the first index then is the row and this is then the column, so we have all columns. Now I could also write the ith column like this, where I take a dot on the row index and then take the ith column, but because we will use columns more often than rows, one index just refers to the column. And so with that notation here, I can say that the kth error of our new error matrix is the same as the transposed error of the kth sample. Okay, and now the idea going forward will be that we will take the old formulas, which are only made for one specific sample, and we will take a look at how we can write these formulas when we take what was previously just vectors as columns of our new concatenated matrices. And the reason we're doing this is because if we think of concatenating all of the individual results of the samples into one matrix, we can also then write this as a result of a matrix multiplication of our newly defined matrices where we have concatenated the inputs instead of concatenating the outputs at the end. Okay, so I hope this made sense. Otherwise, just bear with me. So let's revisit the old formulas then. So first, let's take a look at the derivative of the loss with respect to some weight. And now, since I mean the old formulas, I will also write this as the loss of a single sample, because that's how we did it up until now, right? We only had one single sample. And we had written this as the delta L, but of course of the kth sample, times the ith unit vector times the activation AL of the kth sample and the jth entry from that. And now, if we were to write this using the newly defined matrices, I would write it like this, where we have the kth column of this error, but transposed actually, because we're transposing it back into a row. Then we're taking the ith unit vector and we're multiplying it with the kth column, but the jth row. So it looks something like this. Okay, so that's just to give you a taste how we can write the old notation with the new matrices. And so we had also calculated the DWs, but only for a specific sample. And now the new DWs will be defined as the averaged DKWs. But we will see that in a second. First, the gradient matrix of WL for a single sample was the outer product of the kth error here transposed times AL transposed, but of course of the kth sample again. Okay, and now look at this. This here is just the kth column. And so this is why we pack them into columns, because every time we are using the deltas in our formula, we actually transpose them. And now the notation gets easier because this is just the kth column here. And this here is also the kth column, but we transpose it still. And now let's come to the new definition of our gradient matrix. So if we take DWL, we want this to be the average of all of the other gradient matrices. So we will define it as follows: 1 over m of the sum of all of these other DKWL matrices. And now we can just plug in the result of DKW. I'm just gonna copy that here. But now notice that we're taking the kth column of a matrix and then transposing the entire result. And this is just the same as if we were to transpose the matrix AL and then taking its kth row instead of its kth column. This is what we will do, because this allows us something very nice, namely that this here is just another way to write the result of a matrix multiplication. You can look this up on Wikipedia. I don't know, type outer product connection to matrix multiplication or something like this, and you will see that I can write it down a bit more explicitly. So if we're taking the sum of the kth column and the kth row of B, then this is just the same as the matrix multiplication between A and B, where we have just written it as a sum of outer products. And so this is exactly the same as we have here now. So we can just write this as 1 over m times delta L times A transposed. Now there is another way we could have calculated this number here, which is by going through the loss function again. So alternatively, we could have also gotten there if we had taken the derivative of the newly defined loss with respect to some parameter. So if we had plugged this in, then we would have gotten the differential of this function here. Now I'm just plugging in the definition of our new loss, and then we can pull in the differential into here in front of the scalar and then in front of the sum. And so we would just be getting the differential of this here, which we have already calculated. That's exactly what we have written down right here. So I could just copy this. Let me do that. Now if we simplify this further, we pull out the ith component of the kth column, so we are getting the ith row of the kth column. Well, then actually we don't need the transposition anymore because it's just a scalar value, and this is the same. And now if we were to redefine dwl as the gathering of all of these individual values here in the matrix, then we would get this term here in every single entry. But then we would be able to pull out the scalar and the sum out of the matrix here. So instead of summing and scaling every single entry of this matrix here, it would be the same as taking the average sum of all of the matrices made up of these entries here. So we can pull out the scalar and the sum, and then have these entries here in I and j. But now this here is just again the outer product between two vectors, namely both the ith column of this and the jth column of this matrix, where since this here makes up the indices I and this makes up the indices j, this is the same as taking the column vector delta k times the column alk and transposing it, which, as we have seen before, is just the same as first transposing the matrix AL and then taking the kth row. And so that's exactly the same expression as we had before, which means that we also get the same result, delta and AL transposed. Okay, so these are two ways to get the same result. Now, of course, the first way here, where we just average the resulting gradient matrices, is shorter. But I think it's still nice to verify that if we start with the newly defined loss function and we gather the terms in that way, we still get the same result. Now with the bias, I won't do both calculations again. So let's just define the new dBl as the average of the gradient vectors of the singular samples. And this here was just the transposition of delta L for the kth sample. And so per definition, this is just the kth column of our new delta L matrix, and we cannot simplify this any further. We're just taking the average of all of the columns of our delta matrix. Now, a calculation that's a bit more interesting is when we are computing the delta matrices recursively. So the first delta L minus 1, honestly, nothing changes that much. We can't simplify this any further, so I will just write it down. This is just a product of two Jacobian matrices where each one depends on the sample k, and then we are letting k run from A to M, and so the individual matrices are the same as usual. We're taking the loss with respect to y hat, or more specifically the kth sample, and then we're multiplying this with the partial of y hat k with respect to the previous activation. And what this exactly will be when we take the loss to be the cross entropy loss and the activation function, the last one, to be the softmax, this is what we will be calculating in the next video. But for now we will leave it as this general formula. And now let's look at the other deltas. So what we already know is that the kth column of our new delta matrix was defined as delta L minus 1 from the kth sample here, but transposed. And we had a formula for this, which we only need to transpose in order to get this new column here. And the formula that we had is that we would first get the previous delta, multiply it with W, and then multiply it with the diagonal of FL prime of ZL minus 1, where we are taking the Z of the kth sample once again, and then transposing all of this. And I hope that you know how to transpose a product of matrices. We are transposing each matrix individually and then swapping their order. But if we transpose a diagonal matrix, then it's just the same matrix. So I don't need to change anything here. The only thing I will do instead is write this here as the kth column of the matrix ZL. Then we get WL transposed in the middle. And if we transpose this error here, then this is per definition just the kth column of the previous delta matrix. And so this is what our new expression looks like. Okay, and the last thing we want to do in this video is try to come up with a formula which is equivalent to appending all of these columns here in a single matrix. And indeed, this is possible, but we will have to be smart about it. So let's take a look at what a diagonal matrix does to a vector here. Because remember, this here is a column vector and this here is just a matrix, which means that their product here is also just a column vector. So if we have a diagonal matrix here and we have a column vector, then the result is of course a column vector. But what happens to the individual entries? Well, this here gets multiplied with this in the first entry, but then all of the other entries here get multiplied with 0, right? And it's the same for all of the other entries. This gets multiplied with this, and all of the other entries here get multiplied with 0. So what we get at the end is that we're multiplying all of the individual entries of that vector here with the entries of the diagonal matrix. So this is basically the same as if we were to pack this diagonal matrix into a column vector and taking the Hadamard product with the other vector. And the Hadamard product is just a pointwise multiplication. So this times this, this times this, this times this, and this times this. And now we will be using this in order to compact this formula here. Because let's think about what we want to do. We want to pack this column for every sample k into a matrix where every k stands for a column of that resulting matrix. So what we can do is that we can compact all of these diagonal matrices as we did here. So what I mean is that we are taking all of the column vectors here and packing them into a matrix. Then we are taking all of the diagonal matrices and packing them into the columns of one matrix, and then we're taking one big Hadamard product between the two, which has the same effect as packing all of the resulting column vectors here into a matrix, except that we can now write it as one computation. So the result we are getting is FL prime of ZL minus 1. And now this is new notation, but I think it's even more intuitive than what we had previously. We're plugging in this matrix here and applying this function to each entry of this matrix, which gives us back a matrix of the same dimension. And this matrix has automatically compressed all of the diagonal entries into the columns. And we are taking the Hadamard product with the matrix that we get when we take all of these columns and put them into a single matrix. But this is just the same as appending all of these vectors first into a matrix, which is, no surprise, just delta L, and then taking the matrix product. So this just becomes WL times delta L. And I wrote an equal sign, but this is not equal as was came before. It's equal to what happens if we compact all of the deltas into one matrix. All right, so that's all of the formulas. Let me gather them again in one place so you can copy them if you want to implement them. Okay, so these are the formulas that we can now implement into Python. And again, this is what we will be looking at in the next video. So then, I hope you enjoyed this one and that I'll see you in the next one. Bye! Holy shit, how did I do this? I'm not sure. Oh, I deleted it. Well, that's not good.